Ever find yourself tapping your foot to a song and think, why does this one feel so good? Well, get ready, because today we're diving into a paper from 1993, Resonance Constraints on Rhythmic Movement by Treffner and Turvey. And we might just find the answer. We're going to uncover this hidden connection between math and physics and how our bodies move, so it's going to be a good one.
It really is amazing how, like, something we take for granted, something like just tapping our foot to music, can really, like, reveal so much about, like, how our brains work.
Right. So this paper, it goes into this idea that our brains actually might rely on this mathematical concept. It's called the Farey Tree. And it uses this to choose and switch between different rhythms, you know. Now, I know Farey Tree sounds kind of like Lord of the Rings-y, you know.
Yeah.
But stick with me.
It's actually pretty cool. It's a way to visualize how, like, all these different rhythms are connected, how they relate to each other. So, like, imagine, like, a tree, like a family tree, almost, but for rhythms. And each branch on the tree is a different rhythmic ratio. And at the very top, you have the simplest ratio. That's 1-to-1. So like 1 beat per second. And then as you go down the tree, it branches out to more complex rhythms. So like 2-to-3, 1-to-2, and so on.
So like a family tree of rhythms. So are you saying there's like a math reason why some rhythms just feel more natural to us?
That's exactly what these researchers, that's what they were looking at.
Yeah.
And they basically said that, you know what, humans, we probably just gravitate, like naturally, towards rhythms that are close neighbors, they call them, on this Farey tree. Rhythms with a specific, well, they have a special relationship, a mathematical one called unimodularity.
Unimodularity. Okay. I'm intrigued, but I need like a real world example. How does this actually play out in like how we move?
Okay, well, let's think about like dancing. You're moving to a certain beat, and then the music changes, the tempo changes, and you don't like, you know, stop and think, okay, what's the new rhythm? You know, your body just finds it. And that effortless shift, that might be your brain, like subconsciously using those unimodular relationships on the Farey tree.
Yeah.
It's using that to smoothly transition to that new tempo.
Oh, that's kind of blowing my mind a little bit. So how did they actually test this out in the lab?
Well, they designed a few different experiments, and the first one was pretty straightforward. So they had participants, just tapping their hands along to a metronome.
Okay.
And then the researchers, they shifted the metronome's frequency, and they're watching how the participants adapt their tapping.
So simple enough, but how do you actually measure, like, someone's rhythm?
Well, they used a system, basically, to record the precise timing of each tap, which let them analyze how the tapping frequency, how that changed in response to the metronome shifting. And what's really interesting is they weren't just looking at whether people were on or off the beat, right? They were actually analyzing those specific mathematical relationships between the original rhythm and the new one.
Okay, so they're not just measuring if someone, like, has rhythm.
Right.
But how their rhythm changes in response to a new beat. So I'm guessing they were looking for those, like, unimodular shifts.
That's exactly right. And that's what they found. Like over 85% of the rhythm shifts, they were unimodular.
Yeah.
But to really get this, we need to look closer at the Farey tree itself. Because it's not just like a static thing. There's different levels of complexity to it, almost like floors in a building, you know?
Floors of rhythm. Okay. I'm picturing a rhythmic skyscraper now.
Right.
Okay, walk me through this.
Okay, so think of the ground floor as those simple rhythms, like that 1-to-1 ratio. And then as you go up, each floor, the rhythms, they just get more and more complex, more intricate, you know, larger numbers, more complex relationships between the beats.
So are you saying we're more likely to use those like ground floor rhythms, like the simpler ones in our everyday movements?
That's what they found in this first experiment, yeah.
Yeah.
But they didn't stop there. They wanted to challenge this idea of unimodularity, so they added something physical, like a swinging pendulum.
Pendulums. Okay, now things are getting interesting.
Right, because now we're not just talking about like, you know, abstract metronome beats. Now we're talking about the physical constraints of a real object swinging at its own natural frequency.
I can already sense this is where things start to get like really complex.
It does. But that's where the fun starts. So their next experiment, participants, now they had to coordinate their hand tapping, with the swinging of this pendulum. And they used pendulums with different lengths, which meant obviously they swing at different speeds. And they wanted to see how that would affect the rhythm shifts.
So instead of just like hearing a new beat there now, like feeling it through the pendulum, did that change anything?
More than you might think.
So last time we were talking about how pendulums were added into the mix, and that seems like a pretty big jump from just tapping along to a metronome, right?
It is. It is. And the researchers found that even with that influence of the pendulum, people still showed this really strong tendency to shift to those new rhythms that were, those unimodular neighbors of the original rhythm.
Yeah.
It's like that mathematical structure is like so ingrained in our system for movement that it even guides us when we're dealing with these physical constraints.
So it's not just about the sound of the beat.
Right.
It's about the physical, feeling of it, too. I mean, it makes you wonder if this applies to even more, complex movements, like dancing or playing sports.
Absolutely.
Yeah.
I mean, think about, a basketball player dribbling down the court.
Uh-huh.
The rhythm of their dribble,
Mm-hmm.
it has to adapt to all these different things, right?
Yeah.
Like the movements of the other players, the bounce of the ball, so many things. And it's possible that unimodularity is at play even there, helping them to coordinate their movements, really seamlessly.
Yeah. Okay, I'm starting to see the big picture here, but let's go back to those pendulums for a second. You mentioned they use different lengths.
Right. So each length that has its own natural frequency, like the speed at which it swings, and they wanted to see if that that physical constraint, would influence which rhythms people chose. It did, yeah. So what they found is that the shifts between those lower levels of the Farey Tree, those simpler rhythms, they were more frequent when people were coordinating with the pendulum. It's like the physical constraint of the pendulum. It was almost like encouraging them to stay within those more basic, those more fundamental rhythmic relationships.
So adding a physical element, it actually made their rhythmic choices simpler. That seems kind of counterintuitive.
It does on the surface. But if you think about it from your brain's perspective, when you're doing something complex, like trying to coordinate two things at once, like tapping with your hand, swinging the pendulum, right? Your brain might say, okay, let's stick with the simpler rhythms. Let's reduce the load here, make things a little smoother. It's like a way to simplify a complex situation,
It's like our brains are always trying to find the most efficient way to do things, right?
Exactly.
So with these pendulum experiments, did they just look at how people adapted to the pendulum's rhythm, or did they throw in any curveball?
Oh, they threw in a curveball.
Yeah.
They brought in musicians for their third experiment to see if their expertise would change things up.
Musicians? Okay. Now I'm really curious. I'm guessing they were better at this whole pendulum tapping thing than us non-musical folks.
You'd think so, right? With all their training and experience with rhythm, you'd expect them to be more adaptable, right?
Yeah.
But the results were kind of the opposite.
Wait, really? The musicians were worse?
Not necessarily worse, but they were definitely less flexible in their adaptation. They were less likely to shift away from that original rhythm that the pendulum set, even when it was different from their preferred tapping tempo.
Yeah.
It's like they were more anchored to that initial rhythm.
Yeah. So it's not that they couldn't coordinate, it's that they were choosing not to adapt as much. That's pretty fascinating. What's the thinking on that?
Well, the researchers suggested that maybe musical training, gives you this stronger sense of internal rhythm. Like they have almost like their own internal metronome going, and it's less influenced by those external cues like the pendulum.
So they're more focused on their own beat and less concerned with matching the pendulum perfectly.
Exactly, yeah. Or it could be that all that practice, all those years of practice have given them more conscious control over their movements. They can consciously choose to stick with a particular rhythm even when their subconscious, unimodular instincts might be telling them to switch.
So they're overriding their natural tendencies. That's pretty impressive. It makes you wonder how much of our movement is actually automatic, and how much we can actually control.
That's a great question. And it's one that researchers are still trying to figure out. But this study definitely shows how those subconscious processes, and our conscious control over movement, how they work together.
Yeah.
It's not as simple either. It's always this back and forth.
This whole concept of unimodularity is so interesting. It's making me think about rhythm in a totally different way. But we've been so focused on the details of the experiments, I almost forgot what they were actually trying to figure out. Can you remind us what Treffner and Turvey, what they ultimately concluded about those resonance constraints.
Yeah, their main takeaway was that this unimodularity principle, the one that's based on the structure of that Farey tree, it plays a huge role in how humans choose and switch between rhythms. Mm-hmm. It's like this resonance constraint. It's almost like guiding our movements toward those mathematically compatible rhythms, you know?
So even when we think we're moving freely, there are these underlying mathematical forces at play.
It seems that way, yeah. And these forces, they're not just like, abstract ideas. They have real implications for how we understand, how humans coordinate, how we control our movement, even things like musical perception, how we experience music, and athletic performance.
This is definitely making me rethink my next trip to the dance floor. Now I'll be looking for those unimodular shifts everywhere. But before we get too carried away, we haven't even touched on the circle map yet. What's the deal with that?
The circle map. That's where things get visually interesting.
Okay. It's
a way to actually see those rhythmic relationships, those relationships that we've been talking about playing out. Think of it as like a map of rhythmic possibilities.
Okay, now you've really piqued my curiosity. Let's dive into that circle map right after this. Okay, we're back and ready to tackle this circle map you mentioned. Sounds like this is where we get to actually, visualize all these rhythmic relationships we've been talking about.
Yeah, that's right. So the circle map, it's a tool, and it helps us model how two different rhythms interact, how two oscillators interact, basically.
Okay.
And you can think of one oscillator as like your hand tapping.
Yeah.
And the other one like the metronome beat, or even the swing of a pendulum.
So are we talking about like literal circles on a map?
Not really. It's more about points moving on a circle. So imagine a dot, and it's traveling around a circle. Mm-hmm. And each time it makes a full rotation that represents one cycle of your hand tap.
Sure.
And the speed that the dot moves at, well, that represents the frequency of your tapping.
Okay, so I'm picturing like a dot like zipping around a racetrack. Faster tapping, faster dot.
Exactly.
Yeah.
And now imagine another dot, and this one's representing the metronome, right?
Sure.
And it's also moving on its own circle. And the magic of the circle map is that it lets us see how those two dots, how they interact,
okay,
based on their frequencies.
Okay, I'm with you so far. But how does this tell us anything about whether the rhythms are like syncing up or clashing?
Okay, so this is where it gets really cool.
Yeah.
So if the frequencies of those two dots, if they're close or related in a specific way, they'll tend to like lock together. They'll lock together on the circle map, and that means your tapping stays synchronized with the metronome. But if the frequencies are too different, those dots, they might start to drift apart, and that represents those moments when you lose the beat.
So like when my foot starts tapping out of sync with the music, that's like those dots, they're drifting apart on the circle map.
Exactly. Mm-hmm. And the researchers actually use this circle map to model what they expected to happen, what they expected the participants to do in the experiment. So they plotted those predicted unimodular shifts, those like comfortable rhythm changes, the ones based on the Farey Tree.
Yeah.
And they compared those to what actually happened in the experiment.
And did they line up?
Yeah, beautifully. It was like the circle map. It was like it gave this visual confirmation of those unimodular shifts that they were seeing. Mm. Showed that the participants' movements, they really were being guided by those underlying mathematical relationships, even when they weren't consciously aware of it.
Wow. So it's not just theory. There's like a visual representation of this unimodularity thing actually happening, like in how people move. That's pretty convincing.
It is. And it's not just about, tapping your hand or coordinating with a pendulum. The researchers, they think these principles, they could apply to a whole bunch of different movements that we do. Walking, running, even more complex stuff like playing music or even, having a conversation.
Wait, conversations have rhythm too.
Think about it, the back and forth, the flow of dialogue, the pauses, the changes in pace. It's all a kind of rhythmic dance, know, and maybe, just maybe, unimodularity plays a role in making those conversations smooth and engaging.
Wow, I'm going to be listening to conversations in a whole new way now. This whole deep dive it's been eye-opening, I had no idea that something so simple, something as simple as tapping my foot could be so mathematically complex.
It's amazing, isn't it? It's a real testament to the power of the human brain. We take our movements for granted, but there's so much going on under the surface, stuff we don't even realize.
It makes you wonder, what other like hidden mathematical structures, what else is out there, shaping our everyday lives?
Exactly. And that's the beauty of science, isn't it? Every time we discover something new, it just opens up more questions, more paths to explore.
Well, we've reached the end of our deep dive into resonance constraints on rhythmic movement, and I hope you've come away with a new appreciation for the hidden, I guess you could call a mathematical symphony that's at play in even our simplest movements.
And maybe the next time you hear a catchy song, you'll listen a little closer, tap your foot a little more mindfully, and just marvel at that intricate dance between math and physics and the human body.
Well, until next time, keep those rhythms flowing.